Right now, somewhere in the world, there's a rack of artificial intelligence servers generating enough heat to physically melt its own silicon in just a matter of seconds.
Yeah, it's a terrifying thought, honestly.
Right, because we always talk about the cloud as this, I don't know, this abstract, weightless entity where we just dump our data and run our workloads.
But the physical reality is brutally heavy.
Mhm.
It is hot, it's deafeningly loud, and, well, if the industrial plumbing that keeps it cool were to suddenly fail.
The internet doesn't just go offline, it effectively catches fire.
Exactly.
So today we are taking a deep dive into the software that prevents that from happening. We're looking at what acts as the nervous system for the modern liquid-cooled data center.
And that physical reality is exactly what we are analyzing today.
Mm.
We're looking at a data sheet and some user interface dashboards for Supermicro's SuperCloud Composer.
Or SEC, right?
Right, SCC.
Yeah.
But specifically, we're focusing on its liquid cooling console module,
Yeah.
or LCCM. And the stakes here are just immense.
They really are. I mean, we are moving way past the era where you could just, pump massive amounts of refrigerated air into a warehouse to keep servers running.
Oh, totally. The industry has changed.
Okay, let's unpack this, because if you're listening to this, you likely already understand the concept of PUE, power usage effectiveness.
The holy grail of data center metrics.
Exactly. The industry has been chasing that mythical 1.0 ratio, trying to ensure that every single watt of power entering a facility goes strictly into computing.
Rather than being wasted on overhead,
Yeah.
like spinning those massive CRT units.
Right, those computer room air conditioning systems. But we've basically reached the thermodynamic limits of air cooling, haven't we?
We absolutely have. The shift to liquid cooling isn't just a trend anymore. I mean, it's a hard physics
Well,
requirement.
because water is just so much better at it.
Right. Water is orders of magnitude more efficient at absorbing and transporting heat than air is. But, and this is but the moment you introduce thousands of gallons of fluid into a highly sensitive, high-voltage electrical environment,
You introduce catastrophic risk.
exactly, you're marrying heavy mechanical engineering, so pumps, valves, fluid dynamics, with highly abstract software orchestration.
And that is exactly what we are tracing today. We aren't just, walking through a software manual. We are going to follow a single degree of heat.
I love that framing.
Yeah, we'll trace it from the moment it leaves the GPU, look at how the software detects and manages the physical infrastructure required to extract that heat,
Right.
and then explore how this same platform dynamically restructures the server workloads themselves based on that physical reality.
What's fascinating here is the convergence of disciplines. The LCCM software we are looking at is essentially merging industrial SCADA systems.
Which are what, exactly?
Oh, right. SCADA is the kind of software used to run oil refineries and power plants. So it's merging that with the agility of modern cloud orchestrators like Kubernetes.
Wow, okay, so let's start right at the Visual Command Center. The source material refers to this interface as a single pane of glass.
A very popular term in enterprise IT.
Yeah, they love that phrase. So if you're the engineer on call, logging into the liquid cooling console, you're presented with a hierarchical tree view on the left side pane.
It looks a bit like a standard file explorer, right?
Kind of, yeah.
Oh.
The path we are looking at drills down from USA to a location called BADE, B-A-D-E, and nested under that, we see an active fleet of exactly 11 cooling towers.
And managing a distributed fleet of mechanical assets really requires that kind of unified topology.
Because before this, how did they do it?
Well, in legacy environments, facilities management and IT management were violently siloed.
Violently siloed. I like that.
It's true. The mechanical engineers monitored the chillers on archaic air-gapped terminals down in the basement, while the IT admins managed the server health on completely separate dashboards up in an office.
Right, which usually resulted in a lot of angry phone calls between the two teams when a server thermal throttled.
Exactly. But here, they are unified.
And I have to say, amidst all this highly technical architecture, I just love the naming convention they've used for these towers.
They are pretty catchy.
They really are. We're looking at AquaCool, AquaChill, FrostFlow, HydroFlow, HydroCool, HydroWaves.
It's like a water park.
Right. And then there's LiquidZen, Liquid Ice, and Liquid Frost.
It provides a necessary human-readable abstraction layer, though.
It does. I mean, LiquidZen is vastly easier to communicate during an emergency over a crackly two-way radio than, Tower 7 Rack B.
Absolutely. But behind those names, The dashboard is aggressively technical.
Oh, yeah. It tracks the IP addresses, the product SKUs, which are all listed as LCS, SCLT, and highly specific part numbers.
So it's not just a pretty interface.
Not at all. But here's the column that really caught my eye, and I want to challenge this a bit. It tracks the firmware version.
Right, the firmware.
We see a mixed environment here, right? Some towers are running version 1102 and others are on 1200. Why does a cooling tower have firmware?
It seems counterintuitive, doesn't it?
It really does. I understand it's an IoT device, but fundamentally it's just a mechanical pump pushing fluid. What logic actually needs to be updated?
I'd argue it goes much deeper than just pushing fluid. We really need to shed the mindset that a cooling tower is a dumb mechanical asset.
Okay, fair.
The datasheet explicitly details CDU lifecycle management and cooling tower lifecycle management.
And CDU stands for?
Cooling distribution unit. It operates using incredibly complex PID controllers, proportional integral derivative controllers.
So wait, it's constantly doing calculus to figure out how hard to push the water based on the thermal load?
Precisely that. The firmware governs the algorithm.
Give me an example of when that matters.
Sure. Let's say a massive AI training run suddenly kicks off across a data center.
Okay.
The heat load spikes almost instantaneously. If the cooling tower's pump just slams from 10% to 100% capacity instantly.
Because it's trying to compensate for the heat.
Right. But if it does it instantly, the sudden change in fluid velocity can cause a water hammer effect.
The water hammer.
Yeah, it's a pressure shock wave that can physically shatter pipe fittings right on the data center floor.
Oh, wow. I hadn't even considered the kinetic impact of the fluid inside the pipes.
It's huge. So a firmware update from version 1102 to 1200 might contain a refined acceleration curve for those VFDs, ensuring the pump ramps up smoothly to handle the thermal spike without compromising the mechanical integrity of the plumbing.
That makes total sense. So it's protecting the physical hardware.
Exactly. Furthermore, the datasheet emphasizes SSL security compliance.
Which is critical if these towers are sitting on the network.
It's paramount. I mean, a mechanical IoT device with an IP address is a massive threat vector.
Because it's connected to everything else.
Right. If an adversary compromises the SSL handshake protocol on the cooling tower, they don't even need to hack your database to take you offline.
They just break the AC.
Basically, yeah. They
Yeah.
just send a malicious command to shut down the facility pumps. Within minutes, the servers overheat and shut down. So tracking firmware compliance directly in the LCCM, alongside the workload orchestrator, ensures your mechanical infrastructure isn't the back door into your digital infrastructure.
That immediately recontextualizes this dashboard for me. You aren't just looking at water flow, you are looking at your physical security posture.
Exactly.
And our source material actually gives us a highly detailed look at what happens when that physical posture is compromised. Let's zoom into the sensor reading tab for the tower named Aquachill.
Ah, yes. The incident.
The timestamp here is 2022-02-22. We are dropping into an active real-time crisis.
The telemetry presented here paints a complete thermodynamic picture of the failure.
Okay, let's act as the digital detectives here. If you're on call, the first thing you see across the top of this dashboard is the global temperature header.
What are the numbers reading?
Inlet air is 30.1 degrees Celsius. Outlet air is 35.1 degrees. Inlet facility water is 42.1 degrees. And outlet facility water is 32.1 degrees.
Okay, if we connect this to the bigger picture of heat exchange, those four numbers validate that the core physics of the tower are still functioning.
How so?
Well, the facility water is coming in hot from the data center floor at roughly 107 degrees Fahrenheit, or 42.1 Celsius, as you said.
Yeah.
That water has absorbed the latent heat from the server cold plates.
Right, and it leaves the tower at 32.1 degrees Celsius. So we have a delta T, a temperature differential of exactly 10 degrees.
Which means the water is successfully shedding its heat.
And we see where that heat is going, right?
Exactly. The ambient air enters the tower at 30.1 degrees and exits hotter at 35.1 degrees.
So the heat is being effectively transferred from the liquid medium to the gaseous medium.
Yes. The specific heat capacity of water is high, meaning it can hold a lot of thermal energy, and the tower is successfully stripping it away.
But despite that successful thermal transfer, the system is screaming. In the main status tiles, we have a glaring red text displaying error under the facility pump status.
That's never good.
No, it's not. And directly below that, the basin level sensor is throwing a red overflow warning.
Those two alerts are intrinsically linked. In fluid dynamics, an error in circulation almost always manifests as an accumulation issue.
Let me feed you the rest of the telemetry on the screen because there are some strange contradictions here.
Okay, let's hear them.
The spring pump operation is off, but the spring pump status is listed as good. The operation mode is glaringly set to manual.
Manual mode, interesting.
Yeah. And the fan VFD status and the control module are both reading good.
The granular metrics at the bottom are where we can diagnose the root cause.
Okay, let's look at the facility column first, since that's where the error is. The facility pump's VFD speed is running at 70%, and it's drawing 4.5 kilowatts of power.
Okay.
The inlet facility water pressure is 500 kilopascals, and the outlet is 400 kilopascal.
This raises an important question regarding mechanical impedance.
Tell me more.
The VFD is commanding the pump to run at 70% speed. A 4.5 kilowatt power draw at that speed suggests the motor is working incredibly hard, perhaps too hard.
Right. If you're pedaling a bicycle at a steady speed on flat ground, it's easy. If you hit a massive hill, you have to push much harder to maintain that same speed.
Exactly the same principle. The motor is drawing high amperage to maintain that 70% rotation.
Yeah.
Now look at the pressure again.
500 kilopascals coming in, but only 400 kilopascals going out.
Right. A massive pressure drop across a pump that is simultaneously drawing high power is a classic signature of a physical obstruction or impeller cavitation.
Wait, what does that mean in plain English?
It means the pump is spinning, it's eating electricity, but it cannot push the required volume of water through the outlet.
Which explains the overflow. If the water is constantly rushing into the basin from the return lines at 500 kilopascals, but the facility pump can only manage to push it back out at a much lower volume because it's obstructed.
The water has nowhere to go but up.
Wow. So the basin level rises until the float sensor triggers the overflow alert.
The telemetry provides a flawless diagnostic trail. But we also have to account for the human element here. You noted that the operation mode was set to manual.
Yeah, that really stood out to me. Is this a situation where an administrator saw the overflow happening and immediately slapped the emergency manual override to try and take control?
That's one possibility.
Or, and this is the darker scenario, was an engineer running routine maintenance in manual mode, accidentally keyed in the wrong VFD parameters, and actively caused the pump to stall and overflow the basin.
The static screenshot leaves that ambiguous, unfortunately. But it perfectly illustrates why manual operation in highly complex, interdependent systems is inherently dangerous.
Totally. But think about the scale of this. If you are managing 11 towers at this one site, plus hundreds of racks of servers, the cognitive load of watching these specific pressure differentials is impossible.
It really is.
I don't care how good the single pane of glass is, a human cannot sit there waiting for the outlet pressure to drop from 500 to 400 kilopascals.
They absolutely shouldn't. And the LCCM architecture anticipates this. The source material outlines policy-based call alert management under its compliance features.
What does that mean in practice?
The philosophy here is management by exception.
Meaning the software only bothers you when something breaks the rules.
Yes, the telemetry collection is continuous, but human intervention is policy-driven.
So you set up rules beforehand.
Right. An administrator defines a rule set like, if facility pump power draw exceeds 4.0 kilowatts while VFD speed is below 75% for more than 60 seconds, trigger a critical alert.
Oh, I see.
The LCCM executes that logic at the edge. It can fire an SNMP trap, trigger a webhook to a system like PagerDuty, or automatically open a JIRA ticket for the maintenance crew.
Okay, so the system is highly reactive to the present moment. It catches the overflow and pages you.
Exactly.
Here's where it gets really interesting for me, though. Reacting to a crisis means the crisis is already happening. You are already in the danger zone.
You want to avoid the danger zone entirely.
Right. To truly manage infrastructure at this scale, you need to look backward to predict the future. And our source material provides a deep dive into the analytics and telemetry module.
This is where we transition from reactive monitoring to predictive lifecycle management. The UI screenshot provides historical time series graphs covering a 24-hour window from May 30th to May 31st.
And these aren't just simple line charts either. They are correlating multiple disparate mechanical actions.
How is it laid out?
The spraying analytics section stacks color-coded bar charts directly on top of each other along the same timeline. We have spraying pump operation, which just shows blocks of green when it's on and gray when it's off.
It's simple enough.
Right. And right below that timeline is the basin level sensor history, which is green for good, red for low, and purple for overflow.
The visual correlation is the actual feature here. In complex fluid systems, variables are highly coupled.
Right. If you're looking at these timelines and you see that every single time the spring pump turns on, exactly 4 minutes later, the basin level drops to low.
You don't need a degree in fluid dynamics to realize the spray pump is pulling water out of the basin faster than the makeup water line can refill it.
Exactly. You've just identified a system imbalance through visual hysteresis.
But the LCCM goes further by tracking the numerical analog data. Below those timelines, we see line graphs for spraying pump power in kilowatts and pump outlet pressure in kilopascals.
The UI shows a specific tooltip hover state here. At exactly 12:0.26 p.m. on May 30th, the spraying pump power was 1.8 kilowatts, and the outlet pressure was 111 kilopascals.
Okay, keep going.
Why do we need second-by-second historical data of a pump's pressure?
Because mechanical components degrade on a predictable curve. The datasheet explicitly calls out rich analytics and telemetry to enable predictive analytics.
Right, predictive analytics.
Think about the bearings inside that pump or the filters in line with the outlet.
They don't just snap in half randomly, they wear down over months.
Exactly. If you track that data point 1.8 kilowatts to produce 111 kilopascals over a 6-month period, you will see a trend line. As the mechanical resistance increases due to wear, the VFD will have to draw more power, say 2.1 kilowatts, just to maintain that same 111 kilopascals of pressure.
Ah, so the efficiency drops over time.
Yes, the predictive analytics engine runs a regression analysis on that efficiency drop. It calculates the slope of degradation.
So it knows when it's going to break before it actually breaks.
Precisely. Instead of waking an engineer up at 2 a.m. with a red error because the pump finally seized, the software flags the system 3 weeks in advance.
That's amazing.
It says, based on current power-to-pressure ratios, this pump will cross the failure threshold in 21 days.
So you schedule the downtime during a Tuesday afternoon maintenance window. You replace the bearing while the system is calm. You are essentially time traveling to prevent the crisis we just looked at in the Aquachill Tower.
That is the core value proposition of deep telemetry. And we see the same level of granular correlation on the airside analytics.
Right, those graphs map the fan VFD speed percentage against the fan power draw, and critically, it overlays both the inlet and outlet air temperatures and relative humidity.
And what does the tooltip show there?
The tooltip at that exact same time, 12:02.26 p.m., shows the fan VFD speed at 73%, drawing 1.8 kilowatts. The inlet air temp is 26.1 degrees Celsius, and the outlet is 29.1 degrees.
This is a perfect visualization of an automated environmental control loop.
How so?
Well, as the sun rises and the ambient outside air and the inlet air gets warmer throughout the morning, the heat exchange process becomes less efficient.
Because you were trying to cool hot water with warm air instead of cold air.
Correct. The delta T shrinks. To compensate and maintain the required facility water outlet temperature, the system must move a larger volume of that warmer air across the heat exchanger.
Oh, I see.
The historical graph perfectly maps this. As the inlet air temperature curve rises, the fan VFD speed curve rises in lockstep.
So it's adapting in real time.
Yes. The software is dynamically adjusting the physical infrastructure, second by second, to match the meteorological reality outside the building.
Okay, I have to push back here.
Go for it.
If the software is this intelligent, if it knows exactly how to tune the PID controllers, and it knows the exact degradation curve of the pump bearings, and it monitors the weather, why hasn't this fully replaced the facilities team?
It's a fair question.
Why does the SuperCloud composer need to alert a human at all? Shouldn't it just fix the issue?
This raises an important question, and it really touches on a fundamental limitation of software engineering when it intersects with the physical world.
Software can't wield a wrench.
It cannot. The LCCM is the ultimate diagnostic tool, but it cannot physically clear a clogged strainer in a water line.
Right, someone has to physically go do that.
However, the broader SuperCloud Composer engine can take autonomous action on the digital side to mitigate the physical failure.
Oh, really?
This is where the source material transitions from facilities management to intelligent data center management.
Oh, this is fascinating. You're saying the software can't fix the water pump, so it fixes the servers instead?
In a manner of speaking, yes. If the predictive analytics determine that Aquachill is going to suffer a pump failure, or if we are actively in the overflow crisis we analyzed, the SCC engine can proactively interface with the hypervisors running on the servers cooled by that specific tower.
Okay, and then what?
It can execute live migrations, shifting the heavy heat-generating AI workloads away from that specific rack, moving them to servers cooled by liquids in or frost flow, which are operating nominally.
That is incredible. It actively removes the thermal load from the failing mechanical system, buying the human engineer the time they need to go use the wrench.
Exactly. The software and the hardware are in a constant dynamic dialogue.
And that dialogue is facilitated by the architecture mentioned in the next section of our source material. The software requires a standardized language to command these physical assets.
Right, and the datasheet is very specific about this. It states that SCC's robust composer engine orchestrates workloads via northbound Redfish APIs, which, quote, provides seamless integration.
Okay, for a listener who might be an expert in software development but maybe hasn't spent time down in the BIOS of bare metal servers, what is the Redfish API and why is it so critical here?
Redfish is a standard created by the DMTF, the Distributed Management Task Force.
And what did we use before Redfish?
Historically, managing bare metal servers meant using IPMI, the Intelligent Platform Management Interface.
And IPMI wasn't good.
It was archaic, insecure, and highly vendor-specific. If you wanted to remotely reboot a server or check its internal CPU temperature, you had to use clunky, proprietary tools.
Which ruins the whole single pane of glass concept if you have servers from 3 different manufacturers.
Exactly. Redfish was designed to modernize this. It provides a RESTful interface using JSON payloads.
Oh, so it speaks the language of modern web development.
Yes. It allows software like SuperCloud Composer to interact with the raw hardware, querying thermal sensors, changing boot orders, managing storage controllers using the exact same standard web protocols used by modern web applications.
So SCC sends an HTTP POC request, and a physical server 1,000 miles away immediately spins up its fans or mounts a new storage drive.
Yes. The abstraction layer is incredibly powerful, and it enables the frictionless deployments the datasheet highlights, specifically zero-touch provisioning for network configuration and zero-touch OS deployment in seconds.
Zero-touch is a buzzword that gets thrown around a lot, but what does it actually look like in practice under the SCC architecture?
In practice, it means eliminating human interaction from the provisioning pipeline. Imagine a technician physically unboxes a $50,000 GPU server, slides it into the rack, and plugs in the power and data cables.
Okay, they've racked it.
That is the end of the human involvement.
Wait, they don't even hook up a crash cart. No monitor or keyboard.
No. The moment the server receives standby power, its BMC, the baseboard management controller, boots up and broadcasts its presence on the management network.
And the software hears that broadcast.
Exactly. The SuperCloud Composer intercepts that broadcast. Using the Redfish API, SCC instantly inventories the new hardware, pushes down the correct firmware updates to the network interface cards, configures the VLANs on the top of rack switch, and commands the server to execute a PXE pre-boot execution environment, pulling the golden image of the operating system across the network and installing it.
In seconds, as the datasheet claims.
The configuration happens in seconds, yeah. The OS deployment is bottlenecked only by the network bandwidth, but the core concept is total automation.
Which removes human error.
Completely. You eliminate configuration drift, human typos, and the massive lag time of manual provisioning.
But the most radical concept in this document isn't just provisioning a server quickly, it's changing the definition of what a server actually is.
It's a huge paradigm shift.
Under device scaling of resources, the source states that SCC manages resource pools in a composable disaggregated infrastructure, supported by a software-defined node composer.
That's a lot of terminology.
Okay, let's unpack this. What is composable disaggregated infrastructure?
It is arguably the most profound architectural shift in data center design in the last decade. Historically, compute infrastructure was monolithic. You bought a pizza box server.
Right, a standard 1U or 2U server.
Inside that metal chassis, you had 2 CPUs, 512 gigabytes of RAM, and 4 NVMe storage drives. Those resources were permanently bound together.
Trapped in the box.
Yes. If you deployed a database workload that required massive amounts of storage but very little CPU power, you utilized the NVMe drives, but the expensive CPUs sat completely idle.
They are stranded resources. You paid for them, you are powering them, you are cooling them, but you can't use them.
Composable disaggregated infrastructure shatters that monolithic box. The architecture physically separates the resources into fluid pools across the network, often utilizing ultra-high-speed interconnects like PCIe over Fabrics or CXL Compute Express Link.
So you literally have a whole rack that is just CPUs, another rack that is nothing but petabytes of NVMe storage, another rack of just GPUs.
Correct. The resources are disaggregated. Now, enter the software-defined node composer. When a user requests a machine for a specific workload, say, a heavy AI rendering job, SEC intercepts that request.
It doesn't look for an empty physical server, does it?
No, it doesn't. It dynamically reaches into the pools and logically composes a bespoke virtual bare metal server on the fly.
Wow.
Grabs 64 cores from the CPU pool, 2 terabytes from the memory pool, and 4 GPUs from the accelerator pool, and binds them together over the high-speed fabric.
To the operating system, it looks like one massive physical computer, but the physical parts might be scattered across 3 different racks.
Yes, and the moment the rendering job finishes, SEC dissolves the node. It returns the CPUs, RAM, and GPUs back to their respective pools, making them instantly available for the next workload.
That's incredibly efficient.
It completely eliminates stranded resources and maximizes asset utilization.
That is wild. It's like having a warehouse full of raw materials and an automated assembly line that can build a sports car in 10 seconds, and the moment the driver steps out, the car disassembles itself back into raw parts.
That's a perfect analogy.
But the datasheet also emphasizes third-party vendor support in this composable environment.
This is a critical business strategy for Supermicro. Composable infrastructure is complex, and many early iterations were strictly walled gardens.
Right.
If you bought into Vendor A's composable fabric, you could only buy Vendor A's hard drives or memory modules.
Vendor lock-in, the absolute bane of enterprise IT.
By explicitly supporting third-party devices, SEC allows an enterprise to protect its existing investments. They can compose nodes using Supermicro compute sleds bonded to legacy third-party storage arrays.
Which makes it way easier to justify buying it.
It expands the available resource selection and drastically lowers the barrier to entry for adopting this disaggregated architecture.
Okay, I am going to play devil's advocate here.
Please do.
I am looking at this entire stack. We have zero touch OS deployments happening in seconds. We have software-defined nodes assembling and dissolving themselves dynamically. We have Redfish APIs manipulating bare metal hardware instantly.
That's a lot of power.
Is this level of automation actually safe? If it only takes seconds to reconfigure a network topology across an entire POD, couldn't a junior engineer with a bad script accidentally wipe out the entire data center storage pool before anyone realizes what happened?
It is the ultimate double-edged sword.
Yeah.
When you remove the friction from deployment, you remove the friction from catastrophic failure.
Right. Things break just as fast as they build.
This is why the management plane must be guarded with extreme prejudice.
And the datasheet addresses this in the compliance and governance section. Along with the SSL security we talked about, it mandates user-defined role-based access control.
RBAC. This is the implementation of the principle of least privilege. In a fully automated, composable environment, identity and access management are your only defense mechanisms against internal errors.
So it's not just a master password for the whole system.
Far from it. RBAC allows you to mathematically restrict the blast radius of any user or script.
The blast radius, I like that term.
A facilities engineer might have full read-write access to the liquid coolant console module to change VFD parameters, but they are hard-locked out of the node composer.
So they can't touch the servers.
Exactly. And a junior developer might be allowed to compose a node from the resource pool, but only up to a maximum of 16 CPU cores, and they absolutely cannot touch the top-of-rack switch configurations.
You are gating the automation. The system can still go incredibly fast, but only on the specific tracks you've authorized for that specific user.
It ensures that the velocity of automation doesn't outpace the governance of the organization.
Which transitions us perfectly to how an organization actually acquires and justifies this kind of sweeping technological shift.
It's not a small undertaking.
Because if you are an IT director listening to this, you don't just buy a composable, liquid-cooled data center on a corporate credit card.
Definitely not.
Let's look at the economics and the sustainability, which the datasheet frames under savings in CapEx OpEx.
The financial model of liquid cooling requires a total paradigm shift. CapEx, capital expenditure, represents the upfront investment.
And it's high, right?
Very high. Retrofitting an existing data center or building a new one with liquid cooling infrastructure is highly capital intensive.
Right. You are buying miles of specialized stainless steel piping, massive multi-story cooling towers like AquaChill, highly complex cooling distribution units, and blind mate dripless manifolds for every single server rack.
It's a massive plumbing project.
It is. The CapEx is undeniably higher than just buying traditional servers and dropping them in an air-conditioned room. However, the OpEx, the operating expenditure, which is primarily your monthly power bill, plummets.
Let's break down the physics of why that OpEx drops so dramatically.
Okay, let's do it.
It comes back to the PUE and the specific heat capacity of water. Pushing cold air around a vast 100,000 square foot facility requires massive industrial blower fans.
Because air just isn't great at holding heat.
Air is a terrible thermal conductor. You have to move enormous volumes of it to remove a small amount of heat, and those blower fans consume staggering amounts of electricity.
Plus, the air constantly mixes. The cold air you just spent money to refrigerate immediately mixes with the hot exhaust air from the servers, ruining your efficiency.
Exactly. Liquid cooling, specifically direct-to-chip cold plates, captures the heat directly at the source, the CPU or GPU die.
So the water is touching the hottest part?
Essentially, yes. Water is pumped directly over the hot silicon. Because water is roughly 3,500 times more volumetrically efficient at storing heat than air, the pumps required to move the fluid consume a fraction of the electricity compared to massive air blowers.
So you spend more money up front on the pipes, but your monthly electricity bill drops so drastically that the ROI, the return on investment, eventually crosses over.
The OpEx savings over the 5 to 7 year life cycle of the hardware more than absorb the initial capex shock.
That makes sense.
But there is a secondary, arguably more critical benefit to this efficiency, which the datasheet explicitly states Supermicro's innovative liquid cooling technology reduces power usage and lowers carbon emissions from fossil-fueled power plants.
This is where the local data center impacts the global grid.
We have to remember where the electricity comes from. For most data centers globally, the grid is still heavily reliant on natural gas or coal.
Right.
By drastically lowering the PUE, by shutting off those massive air conditioners, the data center physically draws fewer megawatts from the local utility.
You are directly preventing tons of carbon dioxide from being emitted into the atmosphere.
Which is no longer just a nice public relations talking point.
Oh, absolutely not.
For publicly traded enterprise tech companies, meeting ESG, environmental, social, and governance mandates is a board-level requirement. Governments are increasingly regulating data center power consumption.
So they don't have a choice.
Liquid cooling, orchestrated by software that aggressively optimizes every single watt like the LCCM, is becoming a regulatory necessity, not just a technical luxury.
It's a profound shift in how we view these massive facilities. They aren't just giant calculators, they are massive consumers of natural resources, and managing their efficiency is critical.
Yes.
So how does Supermicro actually sell this massive software suite? The datasheet details a specific license structure.
There are 3 primary license models detailed here. First is the monitor license, with the part number SFT SDDC single. This is a per-node license.
So you need one license key for every single server or endpoint managed by the SEC software.
Correct. It scales linearly with your infrastructure. The second is the DCMS license, part number SFT DCMS single. The source states this is required to enable advanced BMC features in SuperCloud Composer.
We talked about the BMC, the baseboard management controller, earlier. What constitutes an advanced feature that requires an upgraded license?
Basic BMC features might include reading temperatures or rebooting the node. Advanced features unlocked by the DCMS license typically involve deep, out-of-band management.
Like what?
This could include automated mass firmware flashing across thousands of nodes simultaneously, deep hardware-level telemetry gathering for the predictive analytics we discussed, or advanced security features like securely erasing NVMe drives remotely before decommissioning a server.
It's the keys to the kingdom for the actual hardware lifecycle. But the third license is the one that really stood out to me.
The trial license.
Yes. The datasheet prominently advertises a free 90 days trial license with full functionality activation, part number SFT SDDC trial. And they even include massive QR codes on the document right to the application page.
They want to make it easy.
I have to ask you about the psychology of this. If an enterprise is going to adopt composable infrastructure and liquid cooling, that is a multi-year, multi-million-dollar architectural shift. Who on earth evaluates that with a 3-month free trial?
If we connect this to the bigger picture, you have to view it through the lens of risk mitigation. Enterprise IT architects are inherently and rightfully paranoid.
Sure.
Ripping and replacing their entire management plane is a career-ending move if it goes wrong. The 90-day trial is not designed to migrate the entire enterprise.
So what are they doing with it?
They are establishing a blast radius. They will carve out a small isolated sandbox, perhaps a single new rack of servers, or a single cooling tower. They install SCC in that sandbox using the full functionality trial.
Proof of concept.
Exactly. The trial allows the engineering team to physically validate the marketing claims. They execute a zero-touch provisioning workflow and time it. They intentionally stress a pump and watch the liquid cooling console module generate the predictive analytics telemetry.
They prove the OPEX savings internally.
Yes. The trial overcomes the initial friction of adoption. Once the engineering team generates hard data, proving that SEC successfully orchestrates the Redfish APIs, manages the composable resource pools, and provides actionable telemetry on the cooling towers.
They can take that to the board.
They have the empirical evidence required to request the multi-million-dollar budget for the full monitor and DCMS licenses. It is a highly effective enterprise sales strategy.
Lowering the barrier to entry so they can prove the massive value on the back end. Well, as we begin to wrap up this deep dive, it's incredible to look back at the sheer scale of the mechanics and logic we've traced today. We didn't just look at a dashboard.
We trace the entire operational reality of the modern data center.
We started by looking at a unified interface, mapping out massive mechanical assets like AquaChill. We acted as detectives diagnosing a high-pressure, high-power pump failure causing a basin overflow.
Right.
We saw how predictive analytics can track the wear on a pump bearing to prevent that failure weeks in advance.
And we explored the software layer that makes it actionable, the Redfish APIs enabling zero-touch provisioning, and the profound shift toward composable disaggregated infrastructure, where servers are assembled and dissolved from fluid resource pools on demand.
All while balancing the strict RBAC security policies to prevent catastrophic mistakes, and ultimately tying it all back to the global electrical grid, understanding how liquid cooling drops OPEX and carbon emissions.
It is a remarkable synthesis of disciplines. But based on the implications of this hyper-efficient heat extraction, there is a fascinating future trajectory we haven't touched on yet.
Oh, where does this go next?
Well, consider what the LCCM is actually doing. It is capturing massive amounts of thermal energy from dense AI clusters into a highly controlled, high-temperature liquid medium.
Right.
We saw the outlet water leaving the tower at roughly 32 degrees Celsius, and often it can be much hotter. Currently, that heat is treated as a waste product expelled into the atmosphere.
Right, the towers just blow it away.
But as platforms like SCC allow us to manage these thermal loads with extreme precision, we are seeing the dawn of district heating integration.
Wait, taking the hot water from the data center and sending it where?
Directly into municipal heating grids. Instead of building data centers in remote deserts, future architectures are placing them in the center of dense urban environments.
Oh, wow.
The data center runs the AI workloads, the liquid cooling system captures the immense heat, and SCC manages the precise flow of that hot water into the pipes that heat adjacent apartment buildings, hospitals, and greenhouses.
So the data center effectively becomes the municipal furnace for the city?
Exactly. It creates a perfectly circular thermal economy. The electricity powers the computation generates heat, and the precise orchestration of systems like LCCM allows us to harvest that heat as a utility rather than venting it as waste.
That is an absolutely wild thought. The next time you run a massive query on an AI model, the heat generated by your prompt could literally be keeping someone's apartment warm in the winter. Thank you for joining us on this deep dive. The next time you hear someone talk about the whitelist invisible cloud, you'll know exactly how much heavy plumbing, predictive telemetry, and software orchestration is constantly churning just beneath the surface. Keep questioning how the technology you rely on every day actually works.